Right. We have Hardeep Chahal, who is going to be talking to us about the AutoCHERI effort. So yes, good. Look around, you're like, I wonder if our speaker is here. Our speaker is here. Excellent. Hopefully we'll have your slides up just a moment.
Yes, so I'm Hardeep Chahal. I work for Beam Connectivity, a member of the AutoCHERI consortium. And we've been looking at trying to get CHERI into the supply chain and eventually CHERI chips and CHERI software being used in cars. So ourselves at Beam and the guys at the University of Exeter, we've been looking at actually implementing CHERI in a demonstration, looking perhaps at the lower level features of getting CHERI integrated. Atlas Idiada and the others at Swansea University have been looking at perhaps a higher level, what changes need to happen in the whole integration of the car, looking at regulation, yes, and general consumer demand. The guys at Catapult Compound Semiconductor Applications, they've been helping us engage with industry, setting up meetings, helping engage discussions in terms of what are they actually looking for in the industry. So getting straight into it, I will talk about a few of the findings we've found. So we've seen how much memory safety plays a role from the figures from Microsoft and Google and others. So we thought, okay, we'd have a look at how big of an issue it is in the automotive industry. It's very closed source, the automotive industry. People don't like to talk about what they're actually doing, let alone any mistakes they've made. So what we decided to do is look through the National Vulnerability Database, specifically automotive vulnerabilities that were raised. So looking at vehicle OEMs such as Jaguar Land Rover or BMW, software applications, so those who produce software stacks such as AutoCHERI or other integrity software such as Green Hills, and down to firmware drivers, so people who make the actual hardware chips, NXP, Renesas, yes, ST, and Infineon and the like. Extracting all that information and putting it together, we end up with the chart on the right. So the inner donut is the types of vulnerabilities and the quantity that we found. So they include integer overflows, double freeze, stuck in forever loops. It's not just memory safety. So there are issues that CHERI isn't designed to solve. So there are sadly 40% that wouldn't have benefited if the chip was CHERI enabled. But there is still a significant amount that was. So 54%, the biggest part of it still being out of bound writes, that the purple one in the bottom left quadrant. The protection with additional mitigations are those which involve the heap, so changes to the memory allocator need to be made rather than just the physical change on the hardware, and the bounds offered in the capabilities. In short, it seems that there is a benefit that having CHERI chips could provide. There are issues and they could be resolved. The majority of the vulnerabilities we found affected the TCU and the infotainment unit. And that makes a lot of sense because that's the areas that actually people use to connect into the car. You don't have direct access to the brakes, so researchers, attackers, penetration testers, they're the bits that use. So the USB port in the infotainment in the front of your car, whether it's Bluetooth to play music from your phone or the actual mobile apps that car vendors provide. But yeah, so it seems like initially it does seem like there could be area for CHERI. Digging a bit deeper into the specific numbers for chip vendors, I thought this graph was interesting. So it focuses on reported vulnerability trends from 2013 to 2023. For Qualcomm, Infineon, Microchip, and Xilinx, you can see specifically from 2013 to 2017, the numbers are very low. single digits, I think they all were. But from 2018 onwards, Qualcomm's reported vulnerabilities shoot up to 150 plus. And that continues. I don't think Qualcomm made as many areas suddenly out of nowhere. Looking into it, the vulnerabilities were reported with email addresses with a Qualcomm suffix. So it turns out Qualcomm probably changed their disclosure policy and started reporting it themselves. Can't say for sure about the others, but you never know how these numbers would change on the grand scheme if Infineon, Microchip, and Xilinx were also to do the same. A different approach at looking at where Cherry could fit in is looking at ECU classification. So beam connectivity, we make telematics units. We thought, okay, from the previous reported vulnerabilities, it makes sense to look at that because that's where the vulnerabilities are found. But the car's a complicated system, and there's lots of other parts that do other functionality sometimes with a lot more regulation involved. So on the left column, hopefully you can read it, you can see different application classes of ECUs. So some are safety related, some are to do with ADAS, some are to do with anti-theft or electric vehicles management. A few example ECUs are given in the second column. And the others are different ways to categorize them. So use cases in terms of what their functionality is, impact category, who's going to be affected by it, seeing who is going to take the blame, who would benefit from it. And then perhaps more software focused, actually getting it involved in the tool chain, what operating systems are used, what software development processes are used. So you can see, looking at the use cases, safety related is usually vehicle motion. That comes with a lot of regulation, and it makes sense. The impact category affected is safety. You have the EV application class. That's perhaps your battery management. You don't want your car catching fire. So it focuses on that. So it has a bit of safety. At the same time, a bit of privacy. If people can see when you're charging your car, they know when you're at home, perhaps where you go to work, if you can see where that's tracked. So yes, finding a bit more information and seeing how things should be phrased and how it should be targeted. Looking more at the software side, so you have the operating systems. As you can see, the majority is AutoCHERI and RTOS. They cover the most boxes in the columns. So they're the people you want to talk to. Most ECU manufacturers and OEM vehicle manufacturers, they want to perhaps focus on the higher safety regulations of the whole system rather than the lower actual code that's being written and hardware issues that might come about if you end up changing your chip. So they try to add a layer of abstraction, rely on AutoCHERI to do that. So you go to your AutoCHERI provider and you ask them, okay, can you work with this chip? They'll go away, they'll produce something and offer it to you. So if you want to try and get Cherry involved in a vehicle, AutoCHERI seems like a good way to do that. But there are others. So there are other artists being used. Some people write their code in bare metal. Again, all those are perhaps for the safety-related EVs, anti-theft ECUs, and the more feature-rich operating systems, QNX and other, which include Linux, Android, Windows. They're used for cybersecurity, infotainment, and ADAS. So the more ones which require higher processing power and more functionality, really. The software development, although all of the code eventually gets made into a binary to run on the ECU, all of that code, it may eventually be compiled from C code, but all that C code isn't written by humans. A lot of it is generated from model-based software such as Simulink. So people create their algorithm or their and they put it out in Simulink and they test it to see if all the it actually operates as required. They run through their safety scenarios and eventually, yes, rely on that to generate the C code. Again, all of this is specifically to avoid issues arising in software. They're trying to rely on automation to remove it. So the key takeaways that we were focusing on is that the TCU is not safety critical. It's probably a bit easier to get change to a Cherry chip because you don't have to go through all the regulations of proving that it is safe, proving that it won't fail too frequently. And at the same time, it uses feature-rich operating systems, which is what Cherry BSD and previously Android and now Linux ports were being made available for us to use by others in the ecosystem. But yes, moving on. So we actually tried to port our application to Morello. So there's a simple stack of applications that we used, of dependencies that we used, and eventually our application on the top. Some of the issues we faced: single origin provenance, alignment. They were quite easy. They were either found at compile time or as soon as we ran the application, it appeared. The ones that were slightly a bit more difficult to debug: non-provenance, preserving copies, and inter-process communication. Although slightly more difficult, still nothing that would have stopped us overcoming them. All of the issues we faced were in the programming guide, so I would say the documentation was very good, and overall the porting effort to Cherry was made easy. I think that is lends to what Robert was saying at the start. The aim of the game was to try to do it in such a way that it's transparent. You don't need to make many changes to your code. There wasn't a big rewrite required. It was minor tweaks to what was already functioning software to just moving it onto a different chip. Yep. So with everything we found out, porting software isn't too difficult. It seems like memory safety is a bit of an issue. We've categorized our ECUs and our vendors and who we need to talk to. We thought we'd go along the supply chain and see who to talk to. So you have people researching new ideas, whether it's quantum computing or autonomous cars. You have the hardware technology providers, the chip providers, so NXP, Infineon, as I already said. You have the software technology supply chain. So that's your AutoCHERI providers, Siemens, Bosch, and a few others. Your ECU manufacturers, so those who actually produce they take the hardware, they take the software, they put it all together in a little box, and they sell it to your vehicle OEM who buys it, plugs it in, and tries to make a car that they can sell. Yes, the discussions were difficult. The key takeaway is nobody wanted additional security. It wasn't a strong driver. It's not a concern of theirs. But other things that they told us and how to try and bring Cherry to market, some were very informative. They told us about what they're struggling with. They said, okay, if you can resolve this issue, it would help a lot. One of the key issues was context switching and meeting timing constraints. That was a much bigger problem for them rather than memory safety. So trying to frame Cherry in a way that can solve that issue was what we were trying to do. So again, all of this was to do with safety-related ECUs. The ones with the TCUs and perhaps the ones where the vulnerabilities were found were less of an issue. You can just throw a more powerful chip there, but trying to get a more powerful safety-related one safety rated one is a bit more expensive. So that, yes. So what were the key takeaways there? And focusing on where issues came about. I'll come on into a later slide. But information they gave about trying to get CHERI into the tool chain. It's difficult because they have standard tool chains that they don't like to change. They have to do lots of unit tests, lots of static analysis tools. If you end up changing it and changing your software stack and integrating it all, yes, they find it difficult. But it's possible when there are incentives. So and there's reasons for change. So one of the big reasons for change now is electric vehicles. You are getting new ECUs to do battery management. You are getting new ECUs to do or additional features on current ECUs to provide ADAS functionality. That's autonomous driving and assisted something. But yes, all this, what I'm trying to say here is there is an opportunity for the supply chains to change. But that time isn't going to be forever. People are trying to fill that space with ECUs that are coming onto the market now for the vehicle manufacturers to use to put into their vehicles now. A quick overview of why perhaps people don't focus on memory safety so much. They have a lot of other things. So this was an issue with, that's a graph, hopefully you can read it. That's a graph from a paper done by NASA looking into an issue regarding unintended acceleration for Toyota. So a few engineers from NASA were trawling through the Toyota code base, looking at their unit test coverage, running a myriad of static analysis tools, code reviews. Is it easy to read? Is it easy to understand? If that's the case, hopefully there's less chance when an engineer makes a change, there's a bug going to be introduced. And looking at the higher level, so the algorithm modeling, logic modeling, system behavior, how it interacts, is the canvas. If you don't have enough bandwidth and your canvas is too chatty, you're not going to getting messages across in time. You're not meeting those timing constraints. Eventually, yes, and it comes to unexpected errors occurring. They eventually said, yes, we can't guarantee, we couldn't find a bug, but we can't say that there isn't a bug. So eventually, a year or so later, another team came in and they said there was an issue. They did find a path where an error could occur. What that issue was is if memory corruption occurred, so there was a bit flip. Eventually, there was a route eventually to the unintended acceleration issue that people were reporting. So yes, you have the software. What I'm trying to show here is the software development process is very thorough. Memory safety is just one type of issue. They do have bandwidth contention, bus contention, missing locks for concurrent running processes. Yes, a myriad of others, cruise control design that you all need to think about. A few final insights. So security alone wasn't a big enough driver, but there are others that they did talk about. So timing constraints is a big one. Looking into it, what is causing these timing constraint issues? It is the context switches. So that on small microcontrollers, that's done by the MPU. If you write a variable and you suddenly want to change to a different process to use that variable, because it's just been updated, there's a big switch, a big delay in that time to take. So having deterministic memory safety, deterministic is key there because you're in a safety critical system. If you want to perhaps replace the MPU with something that's much faster, it has to have the determinism and the safety rating and documentation to prove that it does what you want it to do. So yes, there are areas that CHERI could provide. So there's two links at the bottom. One's to a paper, a PhD paper that actually delved quite deep into this and highlighted all the benefits of Cherry over an MPU. And the second is somebody complaining about AutoCHERI and the issues they face because that using these software stacks and these auto-generated code from these model-based systems, they add layers which eventually make debugging harder and slow the actual processes down, making function calls that perhaps might be unnecessary. But yes, hopefully that gives you guys some ideas on how Cherry should be framed to get increased adoption. Thank you. Got any questions? Yes.
Multiple systems because many events
Yes. So the question was, if they're using small microcontrollers, are they moving towards multi-core systems? Yes, and it's bringing perhaps more headache than they would like. I'm not an expert in this. Like we said, we focus on telematics units, so we don't focus on the safety-related stuff. But as I said, they were very open about the issues they're facing. These memory delays when trying to keep your memory consistent across different cores is a challenge for them. Having to flush and re-enter your MPU registers, yes, this is a pain. But there are there are microcontrollers that are multi-core and safety rated, so they are on the market. People are using them. So perhaps it's a solved system. Are they happy with it? I'm unsure. It's brought different challenges in terms of focusing on timing now. Any other questions? Yes.
So in the supply chain, OEM, it works for both an OEM and one. The only people that really count are the OEM. They're going to drive adoption of the technology. I was wondering which OEMs you talk to. They're probably very different.
Yes. So the question is, in the supply chain, you have tier ones and OEMs. It seems the requirements come from the OEMs onto the tier ones. But the OEMs at the same time perhaps don't have the knowledge or understanding to request Cherry. Is that what you're perhaps saying? Yes, that's true. So we spoke to JLR, so the research team there, they were quite informative. They understood the issues that they were going to face. So perhaps writing high-level application code, they were wondering, okay, who's going to port all of the dependencies? That's what they were focusing on, rather than the actual porting effort of their own code. If they do have to make a change in the dependency, they didn't want to become responsible for maintaining it. Others, such as JCB, are perhaps less technically focused. As the research team at JLR, perhaps we just spoke to a different team. And they were leaning perhaps towards other solutions rather than Cherry. They were opting for Rust, but perhaps didn't understand that the effort involved to port all their software to Rust. It might be okay for new ECUs, but old ones, yes, there's a big amount of software that needs to currently work safely.